everyone, in this video I'm going to discuss quasi-linear utility functions and their demand. This is just part one. I've had to split the video up into two parts, and this is because I'm going to go through two examples, so the analysis is pretty long. Now the reason why I'm going through two examples is because in one example I get two solution types, so I get a corner solution and an interior solution. In the other example I get three solution types, so two corner solutions and one interior. And I found it very illustrative to go through both examples kind of side by side and compare them and find out why we get these different results. But it's turned into basically a whole lecture, so apologies for this. I probably will at some point redo these videos to make them more palatable. In any case, what's done is done. In this video, I'm going to describe quasi-linear utility. I'll especially look at our marginal utilities. I'll look at the indifference curves of quasi-linear utility functions, and then I'll discuss solving for our interior solutions. So I'll do that for both examples in part two, so that will be a separate video. I'll discuss the corner solutions. And this is actually a request, so thank you to the subscriber who requested this video. I'm not surprised that this topic was requested, because if you have a look at the literature, I feel like it's not hugely detailed, especially the corner solutions aren't really discussed much. A textbook that I do find to be good is Donald Campbell's book Incentives. I think Campbell provides a pretty good discussion. At the least, he does discuss corner solutions, and in fact, one of my examples that I'll go through today is an example from Campbell's book. So you can check that out as an additional resource if you need it. I'll put the details in the description below. All right, let's describe quasi-linear utility and discuss the main features of this type of utility function. And well, abstractly, our quasi-linear utility will be a function of two goods. So I'm going to use X and Y for our goods. You can conceive of three or more goods, but let's just keep it simple. One of those goods, let's just say X, will enter into our utility function as B of X, where B of X is a nonlinear function. B of X will need to have a positive first derivative and a negative second derivative. In contrast, Y will enter into our utility function in a linear fashion. Now, practically, this just means that in our utility function, you're just going to see Y, or at most there'll be some coefficient in front of Y multiplying it, but Y will not be raised to any power. We won't have the square root of Y, not the log of Y. All of these things would imply nonlinearity. So for our first example, then you can see utility is equal to X to the power of a half plus Y. So I'm just going to start by checking that this function meets the requirements of quasi-linearity that I just described. And I can see here that X does indeed enter our function in a nonlinear manner. So abstractly, we would say B of X is equal to X to the power of a half. The first derivative of B of X will be equal to, I'll take the half in front of X and take 1 off the exponent. So a half times X to the power of negative a half, and I can rewrite this with X on the denominator like that. In order to take the second derivative here, I'll use our power rule again on that first derivative. So I take that exponent on X, that's negative a half, out the front. That's multiplied by a half times X to the power of negative 3 over 2. I've taken another 1 off the exponent again. Half times a half is a quarter, so I'm left with a quarter and then X to the power of 3 over 2 on the denominator. We've got a negative second derivative and a positive first derivative. Now I should say I do have a playlist which goes through different math skills, so you can check there if you're having any issues with this stuff. Y here also enters in a linear fashion. Its coefficient is 1, so it's not doing anything nonlinear. Another tick, this example meets our requirements of quasi-linearity. The next thing I'm going to think about is the marginal utilities of X and Y. So the marginal utility of each of our goods is going to tell us about how much utility our consumer gets from the consumption of each marginal unit that they consume. We're going to find our marginal utility by taking the partial derivative of our utility function with respect to each good. So the marginal utility of X, well, this will be equal to the partial derivative of our utility function with respect to X, which will actually be equal to the first derivative of B of X that we found before. So that's half times X to the power of negative a half. I'll put X on the denominator again, so we get 1 divided by 2 times X to the power of a half. And if we graph this marginal utility function, it actually looks like this. Now you can use a graphing app to confirm all this, but it's worth just thinking about this yourself as well. So with this function, the idea is that when x is really small, our denominator value will get really small, so our marginal utility is really large. As x gets larger, the marginal utility of x gets smaller because that denominator value gets really large, which renders the absolute value of that fraction smaller. Now in these videos, I'm going to use this sort of logic a lot. So thinking about how a function behaves at various levels of variables. So let's just do an example just so we're clear about the logic that I'm talking about here. So if x was like 0.025, our marginal utility of x will be equal to, well, if we raise 0.025 by a half, that's equal to the square root of 0.025, which is 0.5. So marginal utility is equal to 1 divided by 2 times 0.5, so 1 over 1, which is just 1. But as x increases, as it gets bigger, the value of this fraction will get smaller because the denominator is going to get larger. So if x is equal to 4, for instance, well, 4 to the power of a half is 2, so our marginal utility is 1 over 2 times 2. 2 times 2 is 4, so the marginal utility is a quarter. So when x is small, marginal utility is large, and as x gets larger, marginal utility reduces. That's the idea, and it's all about that x on the denominator. And actually, this means if we think about it, as x gets close to 0, it will get really, really, really high. But it's asymptotic to the axes, it never crosses it. Now we can see this because we cannot divide by 0, so if we substitute x is equal to 0, that would render the whole fraction undefined. But as x approaches 0, we can think that the marginal utility will get really, really, really high. So much so that for the first marginal unit of x that's consumed, we can think of the marginal utility associated with that as being like infinity or something. Now this will be important later on when we think about the existence or the possibility of one type of corner solution. And you can see just thinking more generally about this diagram that the utility gain for each marginal unit consumed, that's always positive, and that's really why we have that first requirement that the first derivative of b of x is positive. But we can also note that our marginal utility is decreasing, and that's driven by the negative second derivative that we had on b of x, that requirement. That really underlies what we call diminishing marginal utility. For each additional unit of x that we consume, our marginal utility is less and less. All right, well, the marginal utility of y, for our first example, will be the partial derivative of our utility function with respect to y, and that's just equal to 1. So it's a constant, and that's really the linear nature of y. The graph looks like this. For each unit that our consumer consumes, the additional utility is positive, and it's always the same. It's always equal to 1. So we have diminishing marginal utility in x and constant marginal utility in y. And so this is a pattern that we will see when we have quasi-linear utility. If you watch both parts of this series, so if you're looking to understand the possible corner solutions as well, so the next video, you will see how critical it is that the marginal utilities have these shapes, how this actually really underlies why we get the solutions that we do when we have quasi-linear utility. All right, before all of that, let's think about our indifference curves of our quasi-linear utility functions. And to this, we can first consider the slope of our indifference curves, which will be the negative of the marginal rate of substitution, the MRS. So thinking about example 1, well, our marginal rate of substitution is the marginal utility of x divided by the marginal utility of y. So that's equal to, we found these marginal utilities before, it's 1 over 2 times x to the power of a half divided by 1. So we just get that 1 cancels out, 1 divided by 2 times x to the power of a half. So the slope of our indifference curves will be equal to the negative of this. Now I'll show you a diagram of these soon, but again, we can just have a look at the equation and try and figure out what's going on. We can see that the slope of our indifference curves, they're negative, so downward sloping. That's to be expected. But we can also see that our curve will get flatter as x gets larger. So the absolute value of this fraction will get smaller as x gets large. Note also that our slope does not depend on y. So the good that enters our utility function in a linear manner, that the slope of our indifference curves does not depend on that good. All right, let's find the equation of and graph a few of these indifference curves to see them a little more closely. And well, each indifference curve will be constructed holding utility constant at some amount. So here, instead of utility, let's put k for constant. I don't know why they use k for constant, but it's always k. It's equal to x to the power of a half plus y. If we take away x to the power of a half from both sides, we get y is equal to k minus x to the power of a half. And this will be the equation of our indifference curves. We can set k to whatever amount of utility that we want. And at this point, I think it's really useful to jump onto a graphing app so that we can graph a few of these. I use Desmos. I'll link to it below in the description. It's a great site in general. And here you can see I have put the equations of some different indifference curves up here on the left, and I've just set k, that level of utility, to 1, 2, 3, 4, and 5. Now we did get predictably some downward sloping curves, and they do get flatter as x increases. And I can see that these indifference curves do cross that horizontal axis, the x-axis, but they don't cross over the y-axis. They actually terminate at the y-axis, but they don't cross over it. And if we zoom in, we can see actually that as these curves approach their intercept, so I'll zoom into when the intercept is 2 for that particular indifference curve, the slope will get steeper and steeper and steeper. And actually our indifference curves are going to get infinitely steep as they approach their y-axis intercept. So just moving back to my whiteboard, I'll just mark these points. So our indifference curves cross the x-axis. They do not cross over the y-axis, but they terminate at the y-axis. They get infinitely steep as x approaches 0. Now we can see the behavior of the slope algebraically by looking at our slope function, which was negative 1 over 2 times x to the power of a half. And so you can see here for our slope, as x gets smaller and smaller and smaller, this fraction is going to get larger and larger in absolute value. That corresponds to a steeper curve. So our slope is going to approach negative infinity as x approaches 0, but we can't divide by 0, so the slope is not defined when x is equal to 0. Now, as for the slope's non-dependency on y, there are a few ways to think about this. One way is to think about, if we fix x at some value, so just here x is equal to 4, well, we can draw a line up, and what this means is that the slope of each of our indifference curves at that value of x, the slope will be the same. So any indifference curve at x is equal to 4 will have the same slope value. And actually we can calculate that slope. We have the equation of the slope. So when x is equal to 4, well, 4 to the power of a half is equal to 2. So the slope is equal to negative 1 over 2 times 2. So at every single indifference curve, at x is equal to 4, the slope is always negative a quarter. So our indifference curves then are essentially vertical translates or shifts of one another. They're exactly the same curve. They're just at different heights. Now, another possible way to think about this that might help is that each x value on this horizontal axis is associated with one unique slope value, and this slope value will be true for every indifference curve at that x value. And this actually has consequences for the nature of our interior solutions when we have quasi-linear utility. That's our next topic. So interior solutions will occur when our consumer consumes a positive amount of each good, and they are found where the slope of our indifference curve is equal to the slope of our budget constraint. So that's the negative of our marginal rate of substitution. That's the slope of our indifference curve when it's equal to the slope of the budget constraint, which is the negative of the price ratios px over py. This just reduces to MRS is equal to px over py. We can take the negatives out on both sides. Now, there are a few ways you can get to this condition. You can take a Lagrangian, you can use substitution in this case, you can think about it visually. I won't motivate this result here. It's the same logic as, say, when we solve for an optimum when we have Cobb-Douglas. This condition is going to make sure we're getting to the highest indifference curve possible given our budget constraint. So, for example, number 1, I can set the MRS, that's a 1 divided by 2 times x to the power of a half equal to px over py. We're going to solve for x. So we multiply both sides by py and then multiply both sides by 2 times x to the power of a half. We're left with py is equal to px times 2 times x to the power of a half. And then we can divide both sides by px and divide out 2 as well, and square both sides to find that x star is equal to py over 2 times px squared. And that's our demand for x. That's the x star if we have our interior solution for this example. Now, to find the demand for y, we're going to substitute this x star back into our budget constraint, which I'll put that up here. That's px, the price of x, times x, plus py, the price of y, times y, is equal to m, our income. So substituting x star, we get px times py over 2 times px squared, plus py times y is equal to m. I'm going to distribute the exponent through the brackets. Now 2 squared is 4, and we see one of those px's cancel out. We can then take away py squared over 4px from both sides, and then we divide by the price of y. And so we find that y star is equal to m, our income, divided by the price of y minus the price of y divided by 4 times the price of x. So that's our demand for x and y when we have interior solutions, for example 1. And straight away we can note that our demand for x does not depend on income. There is no m value in our demand for good x. And this means that there will be no income effect for good x if we have an interior solution. So we can change around income, but the demand for x will not change. It will stay the same. That's not true for y star. We see that m does figure in the demand for y star, so y star will change as m changes. Now let's look at this visually. Our interior solutions will look like this. We have a budget constraint, I've put it in blue, and our indifference curves, I have them in green, and we're trying to get to the highest indifference curve given our budget constraint. We can find that optimal point. That's where our budget constraint is exactly tangent to our indifference curves. So that's what our interior solution will look like. Now, the trick is, though, that the slope of our budget constraint does not change as we change income. And so this means that we can increase income. This will shift out our budget constraint, and it will put us on a new higher indifference curve, but the value of x corresponding to that point of new tangency, that will be at the same x that we had at the lower income level. Because recall, each x is associated with a particular slope value, and that slope is true of all x's across all indifference curves. And the slope of the budget constraint hasn't changed either, so the x associated with the tangency point must be the same. So there is no income effect on x then. We can increase our income, but x star does not change. Now there is an income effect on y. As income increases, y star does indeed increase. And we saw that in our demand equation for y, m did figure in that demand equation, but no income effect on x as long as we have an interior solution. Now there can be an income effect at very low levels of income. This will be a characteristic of one of our corner solutions, so I'll discuss that in part 2. Before we get there though, I'm going to do this whole analysis again for example 2. But we can do this all again quite quickly because we've already done this once before. So in our second example, utility is equal to the log of x plus 1 plus y. Now here, abstractly, b of x is equal to the log of x plus 1, and I'm going to check the signs of the derivatives of b of x. And here, to take the derivative, I'm going to use the chain rule since x plus 1 is like a little function within the overall log structure. And I can do this formally. I'm going to define small g of x as x plus 1, and so we can redefine our function b as b of g of x is equal to the log of g of x. The derivative of b with respect to x then will be the derivative of b with respect to g of x multiplied by the derivative of g with respect to x. So the derivative of b with respect to g of x is going to be equal to 1 divided by g of x. The derivative of x plus 1 with respect to x is equal to 1. So my derivative of b with respect to x is equal to 1 over g of x times 1. And this all reduces to 1 divided by x plus 1. I just subbed x plus 1 back in since g of x is equal to x plus 1. So that's our first derivative. To find the second derivative, I'm going to take the derivative again of b prime of x. And again, this is another composite function. So I'm going to use the chain rule again. I won't write it out formally this time because actually the notation I find gets a bit confusing. So I'll just walk you through it. So x plus 1, that's like our little function, and the larger function is 1 over our little function. Or to say this another way, by putting x plus 1 on the denominator, we're really raising it to the power of -1, right? So to take the derivative of the larger function with respect to the little function, I take -1 out the front, and then I will have over x plus 1 to the power of 2. I've taken another 1 off the exponent. That's where that 2 comes from. And we multiply this by 1, which is the derivative of x plus 1 with respect to x. So this all reduces to negative 1 divided by x plus 1 squared. So we can see we have a positive first derivative and a negative second derivative. So that's perfect. Y here also enters in a linear fashion. So we have met the requirements of quasi-linearity. We can now think about our marginal utilities. The marginal utility of x is equal to, well, the partial derivative of utility with respect to x, which will be equal to that same derivative of b of x for example 2, so 1 divided by x plus 1. And the graph of this marginal utility looks really similar to example 1. We see that characteristic diminishing marginal utility, that downward slope, except, and you can check a graphing app, we do cross the vertical axes. This function is not asymptotic to the vertical axes like in example 1. Now we can check that by setting x is equal to 0 and seeing that the marginal utility is equal to 1. And this will have consequences later in terms of the existence of one of our corner solutions. The marginal utility function is asymptotic to x is equal to negative 1 though, since if we substitute x is equal to negative 1 into our marginal utility function, this would lead that denominator to being equal to 0 and we can't divide by 0, but gets infinitely large as x approaches negative 1. The marginal utility of y for our second example is the partial derivative of our utility function with respect to y, and that's just equal to 1, just like in example number 1. It's constant, it looks like this. So we have diminishing marginal utility in x, but no diminishing marginal utility in y. That's constant marginal utility for y. All right, now let's think about our indifference curves. Just like in example 1, the slope will be the negative of our MRS, and our MRS is our ratio of marginal utilities. So 1 over x plus 1 over 1, so that's just 1 over x plus 1. The slope is the negative of this, so negative 1 over x plus 1. And I can see just by looking at this equation, we have a downward sloping indifference curve, which will again have this sort of shape where the slope gets flatter. The slope does not depend on y. This is a common theme of quasi-linear indifference curves. To find the equation of our indifference curve, we're going to first note that each indifference curve is constructed holding utility constant at some level. So I'll put k for constant, that's our level of utility, is equal to the log of x plus 1 plus y. We can take away the log of x plus 1 from both sides and we get y is equal to k minus the log of x plus 1, and this will be the equation of our indifference curves for example 2. We can set k to whatever amount of utility that we want. So let's go back to that Desmos site, and you can see here I've drawn a few of these indifference curves. I've set k equal to 1, 2, 3, 4, and 5. We get something that's very, very similar to example number 1, except one insight that I can see straight away is that these indifference curves, they cross both our x and y axes. Unlike our first example, which if you remember, it only crossed the x axes, our indifference curves terminated at the y axes. So I'll go back to our whiteboard and I'll write down these points. We cross the x and y axes, and the slope of our indifference curves do not depend on y. So there's no y value in our equation for the slope. And this means, just like our first example, for every x value, every indifference curve at that x value will have the same slope, like I've drawn here at x is equal to 1. And we have that same feature then that our indifference curves are vertical translates of one another. Every x here is associated with a single unique slope value. We can also note that the slope is undefined at x is equal to negative 1. Since setting x is equal to negative 1, that would render the denominator equal to 0. So we have asymptotes to that x is equal to negative 1. All right, let's describe the interior solutions then when both goods are consumed at some positive level. We'll follow exactly the same steps as in example 1. We're going to set our MRS, 1 divided by x plus 1 equal to the price ratio. I'm going to solve for x here. Let's multiply both sides by x plus 1 and multiply both sides by the price of y. And then we can divide both sides by the price of x. So we get py over px is equal to x plus 1. We can then take away 1 from both sides and we get x star, our optimal consumption of x, is equal to py over px minus 1. We can substitute this x star back into our budget constraint and we get, well, the price of x times Well, x star, which is py over px minus 1 plus py times y, is equal to m. Let's open up the brackets here, and those px's cancel out. So we're left with py minus px plus py times y is equal to m. We can take away py and add px to both sides of our equation here. And then we can divide by py, and we get y star is equal to m over py minus 1 plus px over py. So that's our demand for x and for y when we have an interior solution with example number 2. And we can note that just like example number 1, x star does not depend on income. So our income m does not factor into the demand for x when we have an interior solution. And that's really the big result about our interior solutions for our quasi-linear utility. The changes in income do not affect the demand for x for that good that enters into our utility function in a non-linear manner. We can look at this graphically. Our interior solutions look like this. It looks very, very similar to example number 1. And you can see here the idea about what happens to our tangency point as we increase income is the same. When we increase our income, since our prices aren't changing, so our budget constraint remains at the same slope, then it meets the indifference curve at the exact same value of x star. That point of tangency will be at the same x value, just at a higher indifference curve. So the optimal y is different. There is an income effect for y, but the optimal x, if we have these interior solutions, it's the same regardless of income. And so we've seen quite a few similarities here between example 1 and example 2, but there have been some differences specifically regarding the behavior of our marginal utility functions, the marginal utility of x in particular, around the vertical axes. And then in example 2, we saw that our indifference curves crossed the vertical axes. So in the next part, in the next video, I'll talk about what this means for when we're thinking about the possibility of corner solutions here. And, apart from those issues, there's a separate issue of there will be a corner solution when income is very low. So it's an interesting it's a very interesting type of utility function. But that's it for this video anyway. I know it was so long. I'm so sorry. Hopefully it still helped. If it did, please like and subscribe. Have a good one, everyone.